Geometric sequences. These sequences have the property that each term is obtained by multiplying the previous term by a fixed constant r, called the ratio, and in the form of the sequence r to the power n, or a multiplied by r to the power n. The theorem for the geometric sequences: let r be a real number, then the limit r to the power n as n approaches infinity could be one of these three cases, depends on the value of the r or the ratio value. For the first case, if the absolute value of the r less than 1, like r equals 1 over 2, the sequence 1 over 2 to the power n would be in the set of 1 over 2, 1 over 4, 1 over 8, and so forth. Or if r is negative 1 over 3, similar way, which is 1 over 3, negative 3 to the power n, which is in the form of negative 1 over 3, 1 over 9, minus 1 over 27, and so forth. As you see the n term, as you take the limit n approaches infinity, the value approaches 0. The second case, for r equals 1. If r equals 1, the sequence of 1 to the power n would be just the set of 1, 1, 1, and so forth. And at the end, it still approaches 1. And the last case, if r is less than or equal to negative 1, negative 1 to the power n, the sequence will be in the form of negative 1, positive 1, negative 1, positive 1. And when you keep going, the limit doesn't exist. Similar to other cases for r greater than 1 or in a positive quantity, like 3 to the power n, the list will be 3, 9, 27, and so forth. And it approaches infinity, which is, we can say it doesn't exist. So for the case that the r positive or the ratio number is positive, the sequence converges or diverges monotonically, because every time you multiply by the positive quantity, the next term is remain the same sign. So it has single behavior, either non-increasing or non-decreasing. For r is less than 0, when you multiply by negative number, the sign changes to the opposite in sign. So this way we call the sequence either converges or diverges by oscillation. Like this situation, the number goes back and forth between negative sign and positive sign. In this example, we're going to determine whether the following sequences converges or diverges, and describe whether they do so monotonically or by oscillation. Monotonically, that means the R is positive. Oscillation, R is negative. Converges or diverges depends on the absolute value of the R. If the absolute value of R is less than 1, the sequence converges. If the absolute value of R is greater than 1, we say the sequence diverges. So for this case, we have an equals 1.5 to the power n, or we can say the ratio R equals 1.5, which means R is positive. Absolute value of R is also positive. If R is positive, so it's monotonic behavior. Absolute value of R is greater than, actually greater than 1, sorry. Absolute value of the R is greater than 1. So then the sequence diverges because the value gets larger and larger. We can say this sequence 1.5 to the power n is, no, sorry, diverges monotonically. Next one, the an equals negative 0.3 to the power n, that means the r or the ratio value equals negative zero point 0.3. And then we categorize it as r is less than 0, and the absolute value of the r, which is absolute value of 0, negative zero point 0.3, is still less than 1. If the value of the r less than 0, the sign will change back and forth between positive and negative, so the behavior will be oscillating behavior. For the absolute value of the r less than 1, the sequence converges. We can say this sequence, negative zero point 0.3 to the power n, converges by oscillation. The last example, the AAN equals 3 to the power n times 4 to the power negative n. We can rewrite it as the R or one quantity at 3 over 4 or raised to the power n. That means the R for this sequence is, or this geometric sequence is 3 over 4. As R equals 3 over 4, R is positive, absolute value of the R less than 1. If R is positive, the sequence is monotonic. And absolute value of the R less than 1, that means the value approaches to the value 0, which converges. So we can say the sequence 3 to the n times 4 to the negative n converges monotonically.